There are some things in math that are just named very poorly, and calling functions even or odd is, in my opinion, one of the worst. Even and odd functions were a name that was given to say that things were similar to graphs like f of x equals x squared. So let's take a look at f of x equals x squared. And if you were to graph this one again is just a standard parabola. It's a nice U-shaped graph. But really what they are describing by this idea of even is that it's symmetric across the y-axis. In other words, if you were to fold this piece of paper like a book right here across this middle line, it would line up and smack right into itself. So in that sense, if you were to then say, well, let's take a look at g of x equals x squared plus 1, and let's try to graph that, that would be this entire graph where if you plotted it, it would come out one above the x squared graph. So it would be the same parabola shape, but one higher. And this one as well, if you were to fold it like a book across the y-axis, would be perfectly symmetric. So this is also an even function. But this is, of course, where people get confused because it's got the number 1 in it, so it can't be even. Or if I put the number 2 on the outside, possibly that's why it's even. Or it's also got a squared. Well, what if it has a fourth? Or what if it has a -2 up there? Are -2 numbers even? For my intents and purposes, I am strongly recommending that if you ever see the statement even function written in a homework problem or on a test, I recommend that you cross it off and just simply write that it's symmetric across the y-axis. So for example, let's take a look at the function h of x equals the absolute value of x. Again, if you type this into a graphing calculator, or if you're familiar with graphing it by hand, you'll know that the shape of this is going to be a V-shaped graph. And so I'm going to ask you, is absolute value of x an even function? And if you don't know what even function means, this is where we get into some difficulty because people will be looking at this trying to find a number 2 or 4 or 6 or 8, and that's not what it means. It means that it resembles this graph only so much as it has the same symmetry. It's a horribly named title. But yeah, this is absolutely an even function because if I was to take any object on here and I was to fold it over, this dot would fold nicely onto this dot across the y-axis. So it is an even function because it's symmetric. Now, the way that we can show this using some notation is we could try to describe what it means to be symmetric, what it means to have the same height on one side of the y-axis and the other side of the y-axis. And the way to think about this one is to say, well, over here, maybe we have an x value, like the number 2. What's the height going to be at -2? Well, if it is in fact symmetric, that means that the height has to be the same. And it has to be the same not only at 2 or 3, but really at any x value and its opposite x value. So the way we can show that using some symbols is we can explore and say, well, what happens if I look at plugging in x into a function versus if I plug in -x into that function? Well, if I plug in x, any number, into this function, I'm going to get the absolute value of x. Obviously, that's exactly what it says right here. So I can replace h of x with something that has the same meaning and a different appearance. What if I do h of -x? Well, that means that I'm going to be plugging in -x into the absolute value function. And since the absolute value function is just asking what is the distance of a number away from 0, the distance of -2 is 2 away from 0, and -8 is 8 away from 0, and -14 is 14 away from 0. So these all come out to just be that same x value that you have on the left-hand side. In fact, it's always a positive x value that we have, same as the left-hand side. And so if it doesn't matter if I plug in a positive number or its opposite, or a negative number and its opposite, I'm always going to get out the exact same thing. We will call this even. So let's take a look, for example, at this one right here, this g of x. If I plug in g of x and I compare that to plugging in g of -x, well, this over here is going to be x then squared plus 1. This one over here is going to be negative x squared plus 1. Well, if you think of negative x squared has to be positive. So let's use absolute values to show that we're really, really confident that the answer here is going to come out positive, whether x is negative or not. And then we're going to have to eventually add 1 onto whatever that is anyways. What about over here? Well, even if x is a negative number, if I'm squaring it, I again get that positive number, and I can add 1 to it, and sure enough, they are the same. So if I can show that g of x is equal to g of negative x, this is enough for me to say that these two are that this is an even function. Now, if we wanted to take a look at odd functions, as you might guess, they're inspired by something similar. They're inspired by something like the graph, let's say f of x equals x cubed, is because it has symmetry, but this time the symmetry is going to be going through the origin, the center of our graph right here. So what do I mean by having symmetry across the origin? It means take any point, and if you go straight towards the origin, you can go out the other side like a mirror, and you will have the exact same thing somewhere on the graph. That's what we talk about as far as being symmetric across the origin. So in your notes, if you ever see something described as an odd function, you want to cross that out and instead say that what we're talking about is symmetry across the origin. And we're going to call this the basis for odd, which essentially means that we're going to say if you take an x value and you flip the x value to the other side, you should also be taking what used to be a positive height and transforming that into a corresponding negative height. In other words, for any function, if you plug in a negative x value, you will get the same as the negative of if you plugged in the positive x value. So how would this work if you had, let's say, the function f of x equals x cubed? How could we verify all this? Well, let's just try plugging it in. If we have f of x equals negative x cubed, then at the very least over here, we can replace f of x with negative x cubed. So we'll just write in negative, and then we'll put in x cubed. We'll replace the entire f of x there. On the left-hand side, what we're now doing is we are plugging in negative x into f of x. So let's try that out. We're going to do negative x all plugged in to the function of f of x, which says make sure you cube whatever you plug in here. So we're going to cube it. And the question is are these two the exact same? Maybe it's not immediately obvious, but we can expand this out a little bit, because on the left-hand side, negative x cubed means negative x times negative x times negative x. And on the right-hand side, negative of x cubed means make negative x times x times x. All right, so we're getting somewhere. On the left-hand side now, you have negative times negative would be a positive, so this first thing would turn into x squared, and you'd still need to multiply it by negative x eventually. And then you could do negative times a positive would be a negative, and that would turn into x cubed on the left-hand side. That looks good enough. And on the right-hand side, we would get negative of x cubed, which we could simplify to negative x cubed. And sure enough, we have that the inputting of a negative inside the function is the same as looking at the positive input and making the answer negative. There's a lot of kind of backwards and forwards here, but that's why the picture is really, really helpful. All we're saying is that if you have a positive x value, you're going to go up the same amount as the down you will travel when you plug in a negative x value.